Start, everybody.
Yep.
Good morning, everyone who is joining us online. Welcome to the second day of the NEAR conference, and it's my pleasure to invite and to introduce our first keynote speaker of the day. It's Anton Shiriaev. He is a professor at the Department of Engineering and Cybernetics at Norwegian University of Science and Technology, world's renowned scientist, in particular in control of underactuated systems, orbital stabilization, and since the recent time, he is also a scientific coordinator and leader of the new mathematical robotics major at Sirius University in Sochi, Russia. So I will not go for too long on the introduction. Thank you very much, Anton, for agreeing to give a keynote talk at our conference, and please go ahead.
Yeah, thank you very much. It's my pleasure to come to the conference. I plan to come physically to Innopolis and make presentation. I think it's much more interactive, but unfortunately it was not possible. Even though I'm in Russia, I'm physically in Sochi now. I just arrived yesterday night, so it will be difficult to come this morning to Kazan. Okay, anyway, talk today, it's more or less introductory to the topic, but I hope that you will be interested in a subject and specifically for young people to understand what kind of mathematics behind various challenges available in let's say, grasping manipulation and the controlling system with flexible joints and so on. And also, I would like to emphasize certain backgrounds which allow us to use, very recent backgrounds which allow us to use some development which appears in artificial intelligence and knowledge extraction, which becomes very popular in the topic, and make some mathematical background for such development will be very, let's say, intriguing and important, I guess. Okay, plan for presentation today is the following. Most of the time I will talk about examples. I will show briefly one example and then discuss a couple of examples more, and then just to spend the rest of the talk on the formulation of manipulation task, which I can see. And I will start immediately with, let's say, examples which done in a lab in Trondheim. I hope you can see my screen, and you will see movie now, where the robot is expected to perform. Can you see the movie?
Yes, everything is okay.
Okay, so you see, what is the task? Is the robot is have in gripping device a pen, and he need to make a square, and the movie on the right shows that it's feasible. So it means that it's not really very hard job. However, there is some intriguing parts in the development of that machinery. And if I repeat the same task without specific developments behind this, let's say, manipulation or drawing, and use a standard software of, let's say, this is robot ABB, then we will see that very similar operation becomes a bit hard. So, roughly speaking, the robot using standard software will not be able to perform such movement, and immediately. So even though the task could be easily done by a kit for quite advanced and expensive robot, it becomes a challenge. So I can repeat it again. And what we'll see as a, let's say, description, the robot has a pen, and pen, of course, in contact with the surface, and suddenly, and there is, we can assume that there is a point of contact between the pen and surface, and suddenly some physics becomes important and drives the pen out, even though of course, control of the robot doesn't know what happens with the pen. So in some sense, the behavior shown on the left and right are done if we assume that a robot has no eye, for example. So it's like a feeling just by encoders and possibly force-talk sensor for the end effect. Okay, I'm trying to come back to the slides. And this was motivation example to understand what is really interaction tasks. So we need to do certain behavior by a robot which will be in contact with environment. Let's see, okay, just a minute. I need to switch to the slides. Yep. And I will come now to two examples, which I call motivating examples, the conceptual examples, which shows what could be the, let's say, cutting edge of development in the topic and what kind of challenges appear. And we'll start with the simplest example. You could imagine that we have a, let's say, brick which should slide on a table, and we have another device which we can actuate by some force, move it towards a brick, and we would like to, let's say, touch it and move. Clearly, in this situation, we have very similar hypothetical experiment compared to what we have seen in a movie, but the task is a bit different. We would like to move the brick to a certain distance, for example, 20 centimeters to the right. And there is plenty of physics involved in that development, and specifically, of course, I don't like to discuss in details contact conditions between the, let's say, this moving stick and the brick I'm going to move. But I will come with simplified dynamics describing the behavior of these two bodies. So assume that they have only one variable to capture their status. Yeah, there is also various type of features which I don't like to see, like deformation. Clearly, on experiment we have seen in a movie the pen moving on some on a paper which also have some rubber, let's say, cover below. So it means that it will be certain deformations, and maybe one of that effects really divert a pen from the path it should go. But anyway, so I just try to illustrate here what kind of physics behind might be important. But in one set of experiments, we done it successfully. In another set of experiments, we deviate from the path immediately. Okay, what kind of physics you need to know to make such experiment? Of course, we start with Newton's law. So we assume that we have some object we start to move, which is in red here, and its status is x. We apply external force Fa. And then the dynamics of this object will be, let's say, mass of this object times acceleration equal to all forces applied, and we assume there is some friction. And we assume that it's linear friction in velocity. And we apply very standard controller to let's say, move this object, let's say PI controller, where we have certain reference, let's say this variable R of t, and the first term is proportional, and then the integral part of that feedback. And we assume that we would like to, let's say, make our reference as simple as possible, just constant. So nothing specific important here. And if I use such feedback and assume that friction is, as I said, just viscous one, it depends on the velocity of x, which is position of, let's say, stick I'm going to move, then I get dynamics in closed loop written like that. And clearly, we can think about what kind of parameters Kp, Ki should be assigned that such a system is stable. It means that our stick will bring its end to the desired position I0. And to do that, we do simple mathematics. For example, I do Laplace transform of that differential equation and get equations of third order where parameters M1, B, Kp, and Ki now constants. And we know from Raus-Horowitz conditions that stability of that differential equation is related to the real parts of eigenvalues of that third order polynomial, and eventually the conditions for that particular third order polynomial are the following: that they have the same sign, so conditions for coefficients, and since mass is positive, then and friction also, let's say B coefficient should be positive, the Kp and I should be positive to be stable, and product between M1 and Ki should be smaller than product between B and Kp. So this is very basic first year class in control systems. However, we will immediately we will see something which is not typically taught in control classes. Let's say what we expect to have, we expect that at some point when the stick we move will touch the brick we are going to move to the particular position. So this is our main object. And something should change in dynamics of our system. And of course, this object has certain mass M2. And what will be the dynamics? New dynamics will be the same as the previous one. However, we'll have some type of parasitic term, which of course related to the additional mass we have in our system, M2. And let's say, roughly speaking, what is written here, I assume that we have the same variable, let's say, parameterizing the status. So the difference between position of this brick and this will be just constant, and differentiating, we will get 0 twice. So again, what is written here, it's a Newton law. If I total system will have mass M1 plus M2, but I intentionally move this additional component to the right to see that we have a previous equation and some perturbation of that equation. Okay, so now let's try to see what status of that system, how it can be stable or unstable. And let's say stability for that system is now changed. Since we have a new parameter M2, and this is just, let's say, part of the total mass of the system, the conditions for stability will be written as inequality written here. So we have a product of B and KP, and then a product of this change mass. And clearly, we design our KP and KI, we design parameters of our controller in a way that it's guaranteed this inequality. However, it might happen that eventually this property is not anymore hold. And if I don't know exactly the mass M2, what will happen immediately whenever I touch it, I will get exponential instability. So it's a very strange situation that I design my controller following very basic rules in control theory or in robotics. Use PI control typically used for very simplistic system, linear one, and immediately I get some type of, let's say, black and white results, some type of very hybrid nature. Whenever my stick will contact the big wall, let's say the brick I'm going to move, my controller will result in instability. So closed loop system will be chattering. So whenever I detach it, I come back, and then whenever I touch it, I should let's say come to the regime which will be unstable. And surprisingly, instability will be exponential as well. So which is possibly you observe this effect whenever you use a drill, make hole in the wall or whatever. So you need to be very careful how you make holes in the wall or in wood and whatever. So it's really maybe related to that as well. Okay, but again, let's come to some type of mathematics to understand what could we do with that example and how we could handle the choices of parameter of controller, if we can, such that system will be in normal condition all the time. Not only the case when we have free space motion or we are in contact. And I rewrite the system introducing this additional variable, let's say as E, in a format that whenever, so it's again equation of third order, is exactly equation which we get after Laplace transform of this characteristic polynomial. And the right hand side of the equation we have either 0 if we have no contact, or this F, this additional force which appears due to the mass of the brick we are going to move. And I would like to see a bit more than just a mass. It could be another force. It could be some spring effect. It could be more complicated, let's say, distributed contact or any other type of physics which might happen there. But in the case of additional mass, yes. What I forget to say also that what I'm thinking now that we need to have picture what really happens in that example. So we have a plant, our, let's say, dynamics of our rod, which are going to touch a brick. We design controller to move it in space, and this is our now closed loop system. So we cannot change anything more. And suddenly our system becomes really in contact with external environment. And what we're really observing here is that it's not property of control design. So controller is internally stabilizing. However, the conditions of contact such closed loop system experience with environment exhibit instability. Okay, so we need to have this picture in mind that, let's say, our design should be, let's say, qualified for not just internal stability of that closed loop, but for additional conditions which might be a bit tricky. And what I'm going to say, what kind of generic properties of that F? I call this bracket as F tilde, saying that sometimes it's 0, sometimes it's F force, which we know that it's just a function of acceleration and mass 2 of brick. Okay, if I take integral of that product for exactly format of F, because this is M2 times X double dot, I can integrate it and see that this is just difference on, let's say, more or less kinetic energy in beginning at the time t. I'm going to integrate this function. And what is important for me, not really explicit form of that function. What is interesting for me is to see that this integral X dot and E double dot are the same thing. And F tilde, it could be 0 or it depends, contact, not contact condition, or explicit form of this function F. It will be always bigger than certain, let's say, number, which is in our case equal to M2 half minus X dot squared and 0. And let's say this becomes very important and classical representation of uncertainty present in the system. Okay. And why it's interesting thing? It's because I would like to make state space representation of those dynamics to see that really the example I try to treat is can be put in more generic format, which is already, let's say, applied for much bigger class of systems. So we have dynamical system, which is linear, which originally designed as a stable one. So this is, let's say, matrix A of closed loop system. Then we have perturbation, which comes into the certain channel, and we have a certain function f tilde, which represent, let's say, our environment or presence or absence of contact in this particular example, but in general, it could be some type of another environmental force. And what we know about that solution of that linear system is that, and that function f tilde, this is exactly what I said, that I would like to derive this expression like scalar e double dot times f tilde. I rewrite it as, let's say, output of our system, which is now just last component times x, where x is the state of our system. And it's bigger than minus gamma, where this is what we have seen in the last slide. And this is what I rewrite in more generic form, and then make transposition of that. And I call this internal part of that integral as a sigma. This is quadratic form. Yep. Okay, and a bit further generalization that I would like to see eventually our example in such format that we have differential equation written now in vectorial format when we have linear stable dynamical system with perturbation when we have nonlinearity, which comes through this, let's say, column B into the dynamics of our system, where nonlinearity characterized by this integral relation. That integral of this quadratic form sigma, which in general, in our case, is just cross product between certain, let's say, g and x and f tilde, but in general, it could be more generic. So you see, we would like to represent our closed loop system with perturbation in the format which we can use for analysis. And the task now is to understand under what conditions the behavior of that system, let's say, of course, without perturbation, we know system is stable and everything goes as we wish. As we designed the controller, it's okay. But whenever perturbation shows up and bounded and satisfies this, let's say, integral, it's typically called integral quadratic constraint, that solution will be still nearby the original behavior. And this is so-called Bieber stability, bounded input, bounded output stability. This is the simplest stability you could expect, that you cannot guarantee any asymptotic, any orbital, or whatever type of stability, just to stay nearby the original behavior whenever force is absent. But whenever it's present, we still, let's say, we're still nearby the nominal behavior. And what we're looking for it's look like similar to Lyapunov analysis, but in this case, it's written in the form that we don't like to achieve asymptotic stability. So we search for quadratic form P of variable x vector here, such that it's time derivative along solution of that system with any perturbation f. It doesn't matter that it's perturbation of the form I have presented an example. Such with any perturbation f which satisfies this inequality, it is still not positive. It means that whenever I have some value in beginning, I guaranteed by this inequality, if such P exists, positive definite matrix in our case dimension 3 by 3, we don't have a big deviation, not just in position, also in velocity and acceleration. Okay, and of course this derivative of function v I can integrate over the time and I get increment, and this is exactly what I just said, that for any time moment value of function v will be certificate, and it will not, let's say, grow bigger than value of this function in BG on the solutions of our system. Okay, but anyway, so what is a time derivative? An integral of time derivative, I can think about the following, that literally I can differentiate this function v along solution of that system and use differential equation which governs the dynamics, because what I haven't written here is that this is of course quadratic form. I need to differentiate it following the standard rule, and I get the expression here where the expression in bracket is just x dot. So this is right hand side of this equation. And if I, let's say, use now the inequality I get here as well, I can add to that integral of that its quadratic form in x and f tilde. I will get in addition this sigma and plus gamma. We know that in all solutions for our system, this expression is always non-negative. So if I add to that integral that expression, I will just increase the value. I cannot make it smaller. So it means that this will be always bigger. And if I do that and collect terms, so gamma is not important for me. It's a little bit like additional value for certificate. But what is interesting here is what expression appears in integral, inside of the integral. So this is quadratic form in x and f tilde. And this is also quadratic form in x and tilde. And if I open now the expression for sigma and collect terms, I will immediately obtain certain quadratic form in x and f tilde. And what I'm interested now is in understanding to what extent there exists p. I don't know if it exists or not, such that the value under the integral always non-increasing, always, let's say, less than 0 for any, not only solutions of our system, but for any vectors x and f tilde. Is it possible? And this is what I copied here. So I get the expression under the integral as a separate term and say I'm looking for p such that this expression always non-positive for any x and f tilde. X is now in R3, f tilde in R1. And it turns out that this is a classical equation, specific type of singular Riccati equation, and presence of solution of that equation related to the specific property of this linear system, and the format we get generated this expression for sigma. Okay, and this is not surprising. And I would like to reformulate the property that these two equations are solvable as the following. It's a property formulated on the transfer function on our dynamical system, where I'm given A, B, C as constant matrices. And in our case, A is a dynamic linear part of the closed loop dynamics. B is the way we introduce perturbation. U is our perturbation, and Y is a function, and Y is, let's say, some type of output which becomes related to definition of quadratic form. We describe let's say all possible perturbations comes into dynamics of our system. But when such system is passive, or these two, let's say, Luria-Riccati equations are solvable, it's a very well-known result. It should be the following: the G should be stable. It's not strictly stable. It just have no poles on the right hand side. It could have some poles on the imaginary axis. On imaginary axis, real part should be non-negative, and if it has a pole on the imaginary axis, then it should be multiplicity 1. So it means that, roughly speaking, that if I approach the pole of that function whenever omega comes to the pole and multiply by omega, let's say s, but if I take it off the real part, will be omega squared, then I should get positive number. Okay, I think this is something very standard, but I would like to emphasize that we come immediately from example to the property which we formulated as a very, very important and basic result in control theory, that for system to work, to be Bibo stable for our closed loop system, which should be stable both in free space, free movement, and interaction task, the transfer function for our system should be satisfying this property. And it will immediately guarantee that there exists Lyapunov function, which will guarantee this Bibo stability. Okay, let's come back to our, let's say, PI controller. Is it possible to check how to tune KP, KI for this case? So PI controller in Laplace variables will be written like follows. And if I check now transfer function from, transfer function from, let's say, force, from velocity we have in our system to the force, that's exactly what we need to compute. We get the following expression here. So interesting thing, not standard thing in control theory, which we have here, that this transfer function will not be proper or strictly proper. You see, we have here this term, which basically means that it's impossible to realize this transfer function. But again, this is not for control design. It's just for analysis of our system with, in front of various perturbations. And we need to see to what extent this transfer function could be corresponding to the stable, or to the passive dynamical system from this input to that output. And what is clearly seen, and as I said, that we need to check eventually these two properties hold. And as it's clearly seen that we have a term here which have multiplicity 2. And it means that without, whenever we have integral part in the control design, we cannot guarantee any passivity of that dynamical system. And it means that there is, in our example, there is always a certain brick of big mass such that we will get destabilized behavior, even be tuned in good fashion the movement of free space stick to move a brick and use only PI control. So this is interesting results saying that we can from here already observe that there is no some type of structural property of the system. Okay, I repeat what we just learned here, that if our system is linear, then passivity or Biba stability let's say, of closed loop system we have with respect to perturbation and PS in contact are related to passivity of our closed loop system from particular input to particular output. Okay, let's come to a second example. Yes, and this is considered to be valid only for the case whenever we have, let's say, to follow not any reference, but just to the steady state. So desired position R0. Let's come to the second conceptual example, which allows us to show that the arguments we have here can be extended, but under certain restrictions. Suppose that I have mechanical system, and it's fully actuated mechanical system when I have, let's say, number of degrees of freedom, Q1, Q2, Qn, and let's say it's so-called natural of simple form, then I have kinetic minus potential energy, Lagrange on that system. And what is well known, then this function becomes, this sum of kinetic and potential energy becomes total energy of the system because system is time invariant. And if I differentiate the time evolution, differentiate this function along solution of that system, I will automatically guaranteed obtain this passivity relation from input to output. So we, in the previous example, we try to search for, let's say, properties for our closed loop system whenever we have such input-output passivity relation. Here for mechanical system is guaranteed, it's given to us. Okay, this immediately comes to the various, let's say, naive but very powerful arguments. Since feedback interconnection of passive system is stable, okay, this is what we try to implicitly use in the previous example. And since our external object or environment is passive, this is also we try to use in the previous example, the integral of, let's say, acceleration of x times m2 was exactly the way to verify this property. Then we can think about the following control design steps. Okay, so I have certain plant, so it's my, let's say, and I would like to design controller. Of course, plant in my case is some mechanical system, it's a robot. And I design controller such that still closed loop system will be mechanical. So in previous example, with PI controller, we even change number of, we have a dynamical controller which will have odd number of states, so it cannot be mechanical in any way. So here I would like to have structural assumption that controller will make this closed loop system mechanical, and then I try to explore this fact for understanding what could be the interaction of that closed loop system with environment. And what I just said, that since if I would be able to achieve this system to be mechanical, I will have certain, let's say, storage function or internal energy of that closed loop system, and environment is assumed to be, again, passive, then interaction of these two systems will be Biba stable automatically. So, and the Lyapunov function shows up for that immediately. So, and this will be valid for any reference which I can assign, because now it's not about linear system and, let's say, stabilization of particular equilibrium. No, it's now generic fact valid. If it's possible, it will be valid for any reference I can choose. So it means that our controller immediately, let's say, gets some type of incentives what should be done if we expect to have interaction task to be performed. So we need to develop controller which makes a closed loop system equivalent to new mechanical system. Okay, the question now, when it's possible. And let's say trivial observations, of course, it's possible only if I have fully actuated system. So again, to make some type of summary in that example, what we observe is that in the case number one, either we have, let's say, system linear and we come to the equilibrium. And then we could think about test of, let's say, passivity and guarantee that our, let's say, experiment will be stable even if we have these contact conditions. Or we can assume that our system needs to follow any reference and also to be stable even we have this perturbation due to the contact conditions, but then our controller should decide that the closed loop system is equivalent to mechanical system, and it's immediately applied that it's fully actuated. Of course, there are some examples when it's not the case, but this is, let's say, classroom case studies. Okay, this is two interesting questions, but anyway, out of these two questions, we immediately get the concept which we would like to, main object we need to investigate in this topic. So it's called mechanical impedance. It was introduced by Neville Hogan, let's say in 1985, so it's 35 years ago. And I think the status of this development characterized by these two conceptual examples. Of course, there is a number of specific cases when you can use structural properties and various types of transformation, feedback transformation techniques to see how you can reduce one case to another case, case number one or case number two, I can consider. But still, it all comes into analysis of that mechanical impedance when it will be perturbation, let's say, in the contact conditions to our closed loop dynamics. And of course, what I hope that you have seen this definition before, but what I would like to argue now is that we get in two conceptual examples, two different results. We have very powerful result. Let's say we could design, let's say, linear closed loop system with dynamical extensions, whatever we want. However, we need to guarantee some passivity relation, and it's related to the frequency conditions and Luria-Riccati solubility conditions, which can be checked very efficiently through analysis of transfer function. Or we need to transform system very restrict class of, let's say, mechanical systems, let's say closed loop system, which also allow us to now track any reference without really a problem. But now I would like to come to linear analysis, because what happens in the example I showed you with the pen, it turns out that none of the cases are directly applied. So of course this is part of experiment, but since we have certain deflection in the contact between pen and the surface we draw the square, we will get additional degree of freedom, which not really controlled, because I mean we have no actuator on the degree of freedom. Neither we follow by a pen. We bring a pen to the particular constant position at the end. So we follow the square. So it's really agile dynamical behavior. And we'd like to understand what can be done if I would like to analyze by some linearization technique the behavior or perturbation to our closed loop dynamics due to the contact conditions. And this is what I basically have. I hope I have a few minutes to say. Yeah, it's still, let's say, about 10 minutes left. Perfect. So, and this requires certain reformulation of the task. Okay. And I would like to formulate that in a way which very sketchy. So whenever we are going to define, make model-based dynamic manipulation task for robotic system, we of course start with modeling of robot kinematics and dynamics. It's a separate question how difficult and how easy such task can be, but we assume that we're given certain models for that. Then of course we have certain type of calibrating techniques for that models. And you have, let's say, experienced researchers in the room which maybe knows much more than I am here, but this is clearly very important task, and there is a big business behind that. But what is important for me, so given this, let's say, calibrated models and let's say representation of both kinematics, dynamics, and possible constraints, we have certain method for, let's say, searching interesting behaviors. So interesting behavior for mechanical system, for our robotic system, will be certain input which generates certain output, which exists on certain time interval. And of course, typically such, let's say, motion planners or shooting methods or whatever, they will result in unstable behavior. And we would like to see certain feedback which will be able to stabilize such behavior. So it should be consistent with the model and also should be stable in some sense. And we need to understand after that stabilization how to be sensitive to the contact condition present in whenever we have really let's say touch environment or grasping or manipulating some external object. Okay, and one more justification. Of course, before we come to, let's say, control design, I will let's say I said that I will come to certain type of artificial intelligence technique. The interesting issue that for quite many trajectories which we think, to search the trajectories, you can use specific representations. You could, of course, think about time representation of the trajectories. However, and this could be fine for me, but quite often you could make different type of representations, which, let's say, basically describe as synchronization function between degrees of freedom. And what is interesting in this type of representation, of course, they parameterize by finite number of constants, finite number of parameters. Let's say, I don't know how looks, let's say, one of the functions, let's say, as a function of time. Each of the functions, which is now written as a function of time, I know only one of them, and plug into those functions phi1, phi n minus 1, and get functions of time for rest of the variables of rest of the degrees of freedom of my system. So, and it means that to represent behavior, I would need to know, of course, only one scalar function and number of parameters of that synchronization patterns. And what is the beauty of that representation is that if I think about searching that, let's say, searching some functions which I don't know, searching behaviors which I don't know, it's quite often appears to be quite simple. Quite often, in some cases, it could be quite complicated, but quite often it becomes simpler to find the parameters, and you will see that that in that example, if you already tested that, or if you haven't done, I would suggest you to try to do it for some simple examples, where this representation typically require polynomials of order only 2, 3, and it's sufficient, and it will be very compact representation of quite complicated movements. And why I called here neural networks, it's because you can convert this type of search into the certain optimization procedure, and we have examples where you search through neural networks, bed representations, and gradient methods. Okay, now this is one of the possible class of trajectories which can generate. Of course, they will be somehow represented in very strange format, because in that representation you don't understand what is U, but let's say it can be computed from the dynamics of the system. This is why I say that calibration of the model and modeling of the system becomes important. But this also can be used for analysis, for example, behaviors you observe. You observe the human walks sometimes, or human jumps, or human do certain behaviors, or human open a door. You basically try to search for that representation as a synchronization function between his limbs. Okay, and then we come to some type of small technical step in control design, that any controller, whenever you apply it to the move your mechanical system, or not necessarily even mechanical system, will be decomposed into two parts. One part will be feed-forward, which generate nominal behavior. We assume that we found that nominal behavior. And another part will be feedback. So, and this is not uniquely defined operators. For example, you have clearly many feed-forward operators, which are function of, let's say, state of your system, such that it will get on nominal behavior, nominal input. So you could have various, let's say, operators here. However, about feedback, this is what is interesting thing, and this is possibly one of the new things for the audience, which I hope to be interesting. Yeah, by the way, it means that feedback since we generated the whole nominal behavior just by feed-forward feedback on nominal behavior is 0. And then it means that feedback term for controlling agile behaviors will be always function of transverse coordinates. What is the transverse coordinates? Transverse coordinate is a function of system states of q dot, which is 0 on trajectory, non-zero outside. And you could have quite many transverse coordinates for your system, but typically you could have at most 2n-1 independent. So it could be a different type of format of representation. And this is what I'm going to state next. This is a formula which is, I think, most important part of that talk, is that it's a formula suggested by my colleagues, and I will make reference to that in the end of the talk, which represent a format of controller for performing, let's say, or stabilizing or making feedback controller for various dynamical manipulation or controlling system with constraints. So which consists of some linear term depends on the transverse coordinates, and also some term which represent some signal sign function, which becomes again dependent on linear combination of transverse coordinates. So here, and the signum, it's vectorial signal function. So, and what is interesting question here is why I like this formula very much is because you see this first part, typically we consider that as a feedback part which pre-stabilized dynamical system. In fact, it's not anymore necessary. The system with such a linear feedback term, linear in terms of transverse coordinates, can be still destabilizing. However, it should satisfy certain requirements on stabilization of certain sufficient number of directions, such that, let's say, so-called transverse linearization will be stabilized up to certain subspace of codimension equal to number of control variables you have in your system. And then you have here some term which represent eventually some contraction to linear subspace where the system becomes uncontrollable, or not stabilizable anymore. And what is interesting to see here that in generic situations, eventually it's possible to find such weighting coefficient or guarantee that they exist, such that such controller, even not stabilizing by linear feedback, will be stabilizing in combination of linear and this sliding mode type feedback. But what's important is that in terms of the, let's say, artificial intelligence again, so it's guaranteed by that result is that there exists certain feedback and certain parameters which allows you to organize a search, numerical search, through neural networks or any other type of machine learning methods for that gains. And there is analytical results which shows that it exists, and there is and this existence guarantee that this numerical search is successful. So coming back to the, let's say, combination of algorithms, which arguments I presented, I have 3 minutes to stay and 2 slides. So my main message is that there exists a way to jump out of the standard force control environment settings, either for linear or for system which can be transformed by controller into mechanical, or let's say early Lagrange equations, to the new type of arguments where you still have linearization based arguments, but applied for the vicinity, or let's say transverse contraction of dynamics to the trajectories, which is not necessary to be, let's say, equilibrium as it was in the first conceptual example. And arguments presented here, let's say that there is always finite time or finite space representations, parametric representations, either for trajectories, either for, let's say, transverse variables. These variables can be also computed approximately following computation of let's say certain representation of basis functions for original coordinates. So it means that we can also search more convenient, more appropriate representation of transverse coordinates if requested, if you cannot compute it based on the model. And yes, and what I said, I have no more time. There is a way to, let's say, defining parameters of high gain part of the sliding mode part also through, let's say, machine learning methods, even though, let's say, the method itself is still trial and error. We cannot guarantee for some cases that we easily to find it, but it's possible to formulate as a task and to see that systems start to, let's say, search for that representation. But what's most important is that the passivity relation which guarantee BIBO stability, BIBO orbital or BIBO contraction stability for the trajectories of mechanical system now becomes converted to the passivity of transverse linearization. So it means that we're able to combine arguments both in the first and second conceptual example to show how it might work. Okay, I think I almost conclude the presentation. I have only two messages. So let's say currently the materials which I presented is now part of the patent application into Swedish Patent Office made by my colleagues Fridovich and Gusev, Sergei Vladimirovich Gusev. A number of publications now they, let's say, will publish. And the EP, so we accepted the EP soon that if you're interested, I will forward it to you. And also, I'm very much interested to, let's say, experimenting with that results. And Sirius University suggests a number of very comfortable conditions for PhD positions and the young researchers at Sochi. I should say that I enjoyed time here. And if you're interested, you please apply or let's say check conditions on university or forward to your talented students, because it's really very serious support in terms of experiments, a very big salary. And but if you just have direct contacts to me, I have mentioned my email. Thank you very much. I hope it was not too boring. Of course, we have a number of experiments, but I think I have no time for that already. Yep.
Thank you very much for your talk, Anton. I think we have time for one quick question. Are there any questions from the audience, please? So maybe while people are thinking about it, Anton, I have a couple of questions, maybe if you don't mind. If you go a couple slides back to slide 17, in the transverse coordinates you mentioned, right? You need the full state observer for Q and Q dot. Right?
No. Mm-hmm. This is a let's say the formula now brought here. It's a bit provocative because I wrote it in the most, let's say, simple case. Of course, if you come to the transverse linearization, then immediately you will see that you come to the let's say area of linear systems. And in case of course, in case of linear systems, you could have reduced order observers, you could have a full state observers, and so on. So it's not really not very important at this moment. So it's written now like a full state feedback control, but in fact it's not. And in all experiments, of course, we never measure velocities. It's not the case. So it's, yeah. Yeah, but it's also important here to mention that number of transverse coordinates is not necessary to be minimalistic. It could be also excessive. So it simplifies a lot of computations eventually. Yeah. Okay,
thank you very much. And yeah, I have many other questions, but probably it's better if I ask them in person. Yep. To not during the schedule. Thank you very much again, Anton.
Yeah.
For your wonderful talk.
Have a good day. Bye.
You too. Goodbye. And I would like to invite our next speaker to try and test the slides. Okay, Anton Perkin. Can you hear me? Anton?
Yes, I hear you.
Just a minute. I need somehow to how to jump out of that.
Switch on. Okay. Sorry, I need to be. I didn't have opportunity to check my. Okay, now I have.
Yeah, can you please check? Yeah. And while you are checking, so let me briefly introduce Anton Perkin.
So okay. I'm trying to share my screen.
I think I only see a black screen, unfortunately.